Hello everyone, this is Sankhadip from Cheenta, and this is the first episode of our new show, Math-Adda. So before we begin today, before we start discussing the subject matter today, let me first tell you the idea of the show. Adda in Bengali means an informal gathering. It's a part of our culture, really. In Kolkata, you can see in tea shops in the afternoon or in the evening, people coming back from colleges, from work, and they gather there and they discuss everything. They just do from gossip to films to international politics, everything they keep discussing. They have loads of tea, and it's a adda actually is a part of the intellectual culture of Kolkata. Okay, at Cheenta, usually we stick to the contests. Either we prepare for Olympiads or we prepare for colleges, there is always an objective, a course, a format of the test. For that reason, Adda can be missing sometimes. Okay, the idea of just relaxing a little bit, talking further about mathematics, having fun, that could be missing sometime. And this show is aimed at doing precisely that. Now, mathematicians sometimes say that Olympiad math is too much about tricks. And it is true to some extent, because initially it's very different from school math. When you start doing Olympiads, it's very different from school math. But after a certain level, when you get to the national or international level, you'll see there are patterns, there are techniques, and so on. At some level, it becomes a bit mechanical. But it need not be that way, because even when doing Olympiad maths, you get occasional glimpses of higher maths, ideas that you don't really know how to recognize when you are at the Olympiad level, but they are present. But we often don't give the time they deserve to these problems or these ideas, because we have to prepare for a test. Now, this show is precisely for those problems that have an application or connection to things beyond the problem itself. So each week or in each episode, we'll take such an interesting problem and we will discuss about the connections it has to other things. And this is just the idea of the format. As this is an adda, this can encompass everything. It can start from Olympiad, it can go to research math, it can go to history of mathematics, it can go to anything. Sky is the limit. And the viewers can participate as well. I would love to talk to you. And I may bring some guests as well from time to time to discuss math or to discuss life, mathematical life. For you may get to talk with working mathematicians to get to know how life is, how life will be if you become a professional mathematician. Anyway, without further ado, this is from INMO 2010. If I'm not wrong, it's from INMO. It says, define a sequence by A0 equal to 0, A1 equal to 1. And for the other terms, you have a recurrence relation. What is a sequence? Rigorously speaking, sequence is a function, a sequence of real numbers in this case, is a function from the set of natural numbers to the set of real numbers. That means given any natural number, you produce a real number. And instead of writing it as a function, you can choose to write it as a sequence as well. So here, the terms of the sequence are actually like this: A0, A1, A2, and so on. Now the problem is saying this sequence is defined by the first two terms and a recurrence relation governing all the other terms that come after. For example, A3 is 2 times A2 plus A1 using this relation. And what is it? It's 2. 2 plus 0, it's 2. Oh, I'm sorry. I'm supposed to find A2. Fine. I'm given A2 and A1, and I'm A1 and A0. I'm going to find A2. So A2 equal to 2A1 plus A0, 2 times 1 plus 0, and that's just 2. And it goes on like that. Actually, this problem has a first part, but the first part is kind of routine, let's say. The first part only involves some manipulations. And as I just say, that this show is all about things that are not regular. Okay. So I chose to skip the first part. But if you want, you can go to the INMO website and you can try the first part. It's not very hard. Now, the second part says, prove that if 2 power k divides n for some n and some k, then 2 power k has to divide an as well. Now, there are many ways to prove this. There are ways that involve tricks. There are ways that involve more advanced ideas. I am going to use this problem to do something very general, which is the solution of a second order difference equation. A general second order difference equation looks something like this. Say xn is equal to pxn minus 1 plus qxn minus 2 for every n greater than or equal to 2. Okay? So the problem of a difference equation is like this. You're given the first two terms. So you're always given x0 and x1. x0 is something, x1 is something. Now you are asked to find xn for every n. Or this is a formula for xn for every n, but not like this. This is a recurrence formula. You are being asked to find something as a function of n. Okay, a closed form formula, if you want. And there is a nice way to do this in general. It goes like this. Note that the equation is linear. What does that mean? That means if you have two sequences satisfying the same equation, suppose the sequences are Cn and Dn, then the sequence En is also a solution where En is equal to alpha Cn plus beta Dn for fixed scalars alpha and beta. What does that mean? That means for the new sequence, E0 is alpha E0, alpha C0 plus beta D0, E1 is alpha C1 plus beta D1, and so on. So we say the equation is linear if any linear combination of the two solutions is also a solution. And why is this true in this case? It's because you can see E of n is equal to alpha Cn plus beta Dn, and that is actually alpha P Cn minus 1 plus Q Cn minus 2 plus beta P Dn minus 1 plus Q Dn minus 2. We can rearrange this to get P times alpha Cn minus 1 plus beta Dn minus 1 plus Q times alpha Cn minus 2 plus beta Dn minus 2, which is nothing but P En minus 1 plus Q En minus 2. Therefore, the sequence En is also a solution of this equation. Okay? That means, given any two solutions, you can produce more solutions. If you consider the space like capital S be the set of all sequences satisfying the recurrence. What I just told you actually proves that this set has a linear structure. Given any two elements, the combination of a linear combination of these two elements is also an element in this set. Such a space with such a structure is called a linear space or a vector space. And remember what I told you at the beginning, that every problem we discuss in this series will have some connection with higher mathematics. This is the connection. The notion of a vector space is the basic idea of the field of linear algebra. Has connections with linear algebra. And linear algebra is the first subject that you study when you start studying higher mathematics. So this problem is bringing you to the doorstep of higher mathematics. Anyway, we won't get into details of this, but we will explore the structure a little bit more. This is the first observation. The set of all sequences satisfying the recurrence is a linear space, observation number 1. Observation number 2 is that this space corresponds to the set of all pairs of real numbers. Why? This one should be obvious. It's because any sequence satisfying this relation, is completely determined by the first two terms, right? Even the sequence given in the problem, if it said A0 equal to 3, A1 equal to 7, then the resulting sequence would have been different, right? Completely different. Even with the same recurrence relation, the resulting sequence would have been completely different. So such recurrence relations are completely determined by the first two terms. If you give me first two terms, I can construct the rest of the sequence starting from those two terms. Thus, the correspondence goes like this. Given a sequence, you map it to first term, second term. And given a real number, given a pair of real number, say A comma B, you map it to the sequence, the unique sequence, by the way, such that x0 is A and x1 is B. I will leave it to you to check that this is actually a bijection. No, not very hard to see. In fact, it's more than a bijection. It's something called a linear correspondence. Or linear isomorphism. What does that mean? It means if you have two sequences, xn and yn, that satisfy the equation, and if you took a linear combination, which is say alpha xn plus beta yn, and if you check the images of all these sequences, for example, suppose xn gets mapped to A1, B1, yn gets mapped to A2, B2. Then you can check that alpha xn plus beta yn actually gets mapped to alpha A1 plus beta A2, alpha B1 plus beta B2. When such a thing happens, we say that the linear structures on the two spaces correspond. Because R2 clearly also has a linear structure, right? Because you can take A1, B1, A2, B2, you can take their linear combination, alpha A1 plus beta A2 and alpha B1 plus beta B2. It doesn't matter whether you do the linear combination in S or R2. On either side, if you do the linear combination, on the other side, there is a correspondence. I hope I'm being clear. Okay? To do a summary, this correspondence, which sends a sequence to the first two terms, it's not just any correspondence. It's a linear correspondence or a linear isomorphism, because if you take two sequences and you take their any linear combination, then the image of that linear combination sequence is the linear combination of the first two images. Okay? Now, once we know this, this is observation number 2. Once we know this, we can have some fun. In R2, given any two vectors which are not on the okay, this is what I mean. Let's talk about R2. Given, say, A1 comma B1 and A2 comma B2, such that A1 by A2 is not equal to B1 by B2, or A1 B2 is not equal to A2 B1, is not equal to A2 B1. Any other A comma B can be written uniquely as a linear combination of A1 B1 and A2 B2. Why is that? We will see. So suppose we have alpha times A1 B1 plus beta times A2 comma B2 is A comma B. We need to show that it is possible to solve this uniquely for the two numbers alpha and beta, right? And this actually gives rise to a system of equations. Alpha A1 plus beta A2 is equal to A, and alpha B1 plus beta B2 is equal to B. I'm pretty sure that you have seen this before. This is a system of linear equations, system of two linear equations with two variables. And it is well known that this has a solution, has a unique solution, if and only if A1 B2 minus B1 A2 is not equal to 0. I suggest you go back and if you don't remember this, I suggest you go back and you revise this part. Okay? This means, let's take a step back and think about what this means. It means given any two numbers, any two, let's say, vectors, it's the standard way to call these numbers is by vectors. Okay. Given any two vectors in R2 which satisfy something, you can construct the whole of R2 using these two by taking linear combinations. And though this seems very new to you, I'm sure that you have seen this before, where for the special case of the vectors 1, 0 and 0, 1, this is just the x-axis and the y-axis, because any x, y is x times 1, 0 plus y times 0, 1. Suppose xy is here, then 1, 0 is this, 1, 0, and 0, 1 is this. If you multiply this by x, if you enlarge this by a factor of x, and if you enlarge this by a factor of y, then and you add those two, you get this one. This is just a special case, okay? But the general result is this one. So it means given two special elements in R2, you can construct any other element of R2 by taking linear combinations. And the two spaces S and R2, remember S is the space of all sequences that satisfy that recurrence relation. So given these two spaces are linearly correspondent, right? So anything you do on R2 can be transported to S. So this essentially means that if you have two sequences satisfying that equation, of course, says that x0 y1 minus x1 y0 is not equal to 0, then any other sequence which is a solution of that can be written. So suppose you have any other sequence Zn, then there exists alpha and beta such that Zn is equal to alpha xn plus beta yn. I'm doing things on the side of R2. I'm transporting that back to the side of S. Take some time to think about this because this idea might be new to you. Okay? Now we are ready to tackle this problem. What is the equation? Check. AN is equal to 2AN minus 1 plus AN minus 2. So in general, the equation is xn is 2xn minus 1 plus xn minus 2. Now, from what we have seen above, it means if I can find two solutions which satisfy something that relation, something not equal to 0, then we can find any other solution. So it suffices to find two solutions as we like. Okay. Now we'll do this by trial and error. Let us see. Is there a solution of the form, let's say, xn equal to lambda power n, where lambda is some number, some real number? Is there a solution of this form? We will check. So if there is indeed a solution of this form, then we have lambda power n is equal to 2 lambda power n minus 1 plus lambda power n minus 2. Then we can cancel lambda power n minus 2 and get lambda square is 2 lambda plus 1. And I'm sure you have seen this before. This is a quadratic equation. Lambda square minus 2 lambda minus 1 equal to 0. That means lambda is equal to 2 plus minus 4 plus 4 by 2. Which is 1 plus minus root 2. So we actually get two solutions. We get one solution which is say xn equal to 1 plus root 2 power n for every n. And we have another solution which is yn equal to 1 minus root 2 or root 2 minus 1. Actually, root 2 is greater than 1. So, oh no, it's 1 minus root 2, fine. 1 minus root 2 power n for every n. And do these solutions satisfy that thing? X naught y1 is not equal to x1 y naught. We can check. Actually, x naught is equal to y naught is equal to 1, and y1 is 1 plus root 2, 1 minus root 2, and x1 is 1 plus root 2. So clearly we have what we want. We have this condition. That means any other solution can be written in as a linear combination of these two. So any other solution Zn can be written as 1 plus root 2 alpha times 1 plus root 2 power n plus beta times 1 minus root 2 power n. And now the question is, for our special case, actually let's write Zn equal to an, because that's what we want to find at the end of the day, right? We want our sequence which starts with 0 and 1. So let's write an instead of Zn. How do we find alpha and beta? Same routine as before. Instead of doing things in S, go to R2, do things there, and then come back. Okay? So if I can do A1 is, A0, which is supposed to be 0, by the way. If we can solve these two equations, then you can solve the rest. 1 is equal to A1 alpha times 1 plus root 2 plus beta times 1 minus root 2. From here we can find alpha and beta, and the correspondence that I keep mentioning actually tells that you do not need to do for anything else. If you do it for A0 and A1, and then it is assured for the rest. So this actually means that alpha is equal to minus beta, and plugging this in the second equation, we get 1 is equal to beta times 1 minus root 2 minus 1 minus root 2, which actually gives you minus 2 root 2 beta is 1. So beta is minus 1 by 2 root 2, and alpha is 1 by 2 root 2. Hence, our sequence is actually given by an equal to 1 by this. Yay. Now for the second part. If 2 power k divides n, then 2 power k has to divide an as well. How do I prove this from here? Suppose 2 power k divides n. That means n is equal to 2 power k times j. Hence, an is 1 plus root 2 power 2 power k j minus 1 minus root 2 power k j by 2 root 2. Now we need to prove that 2 power k actually divides an, or an need to prove that an by 2 power k is an integer. What is an by 2 power k? It's 1 plus root 2 power 2 power k times j minus 1 minus root 2 power 2 power k times j by 2 power k plus 1 root 2. Now we will do some factorizations. This thing 1 plus actually let's call them let's call this, say, 1 plus root 2 is some m, no, it's some gamma, and 1 minus root 2 is delta. Note that gamma power 2 power k j minus delta power 2 power k j is actually gamma power 2 power k minus 1 j whole square minus delta power 2 power k minus 1 j whole square. And this can be factorized. So this is gamma 2 power k minus 1 j plus delta power 2 power k minus 1 j times gamma power 2 power k minus 1 j minus delta power 2 power k minus 1 j. Then I can factorize this even another time, and more and more and more. So if I keep factorizing in this manner, what I will get is I can break this whole thing down. I can break this whole thing down into a bunch of factors. It's going to look like this. First factor is gamma power 2 power k minus 1 j plus delta power 2 power k minus 1 j by 2. So I have a huge supply of 2's. I'm going to utilize those supplies. Okay. Then there will be a next factor, gamma power 2 power k minus 2 j plus delta power 2 power k minus 2 j by 2. It will continue till the point when you cannot do it anymore. And the last term will be gamma power j plus delta power j divided by 2 times gamma power j minus delta power j by 2 root 2. How many 2's are here? This is actually 2 power 0. Now it starts from 2 power 0 and it goes to 2 power k minus 1. So k2s are here. Here you have 2 number 1, 2 number 2, and so on till 2 number k. And there is another last 2 and the root 2. So it's all fine. Now note that this last term, last factor, this is actually aj. So it is already an integer. I only care about the rest of the factors. And I'm going to make a claim. Gamma power 2 power, say, L times j plus delta power 2 power L j by 2 is an integer always. Always integer. Which means each of these factors is an integer. The final thing, and the last one is aj, of course. The final thing being a product of integers is also an integer. And if you prove that, we are done. Now we are going to break this up using binomial theorem. So it is 1 plus root 2 power 2 power L j plus 1 minus root 2 power 2 power L j. Let us check how the terms look like. The first one, if we break it down using binomial theorem, it's going to be something like this: k equal to 0 to 2 power L j, 2 power L j. Actually, the power of 2 doesn't matter. We can take it to be some m. Just to simplify our calculations, let's call it m. M choose k, 1 power m, then root 2, sorry, k, 1 power k, root 2 power m minus k. And then the second one is k from 0 to m, 1 power k minus root 2 power m minus k. Now, a term like this, a term m choose k times root 2 power m minus k is irrational only if m minus k is odd, right? Because otherwise it becomes a power of 2. When m minus k is odd, then the corresponding term here is actually m choose k minus root 2 power m minus k. So when we add, all the irrational terms pair up and they get cancelled. So we are left with a sum of powers of 2. We are left with a sum which looks like sum of some factor times 2 power something. The first term is going to be the first term is going to be 2, then it's going to be 4, and so on. So the bottom line is, when we add these two, the irrational terms get cancelled, and only the terms are left are all powers of 2. So the whole thing is even. It cannot be odd. Thus, this thing divided by 2 is an integer. So this particular term that we are considering is an integer. Therefore, the whole thing is an integer. Okay? Before we leave today, I would like to draw your attention to two things. First one, say Bn is equal to lambda power n plus delta power n by 2. This is also a sequence which comes from a recurrence relation. Okay, which sequence is that? And what is the recurrence relation for this sequence? Note that if you find this recurrence relation, then you don't need to do this binomial trickery that I just did, because then you will say, look, B0 is this, B0 is actually, you can say it's 1, and I think B1 is going to be, you'll see it's going to be some integer. Then you will say, look, B0 is an integer, B1 is an integer, and we have this recurrence relation involving integers. So Bn is in an integer for every n. Okay, if you do it that way, then you won't need to use this big ugly expansion thing. Okay, this is the first comment. And the second comment is, note that luckily in this case we got an equation here, this equation for lambda here. We got an equation for lambda that has two distinct roots. So we got two distinct solutions, and then we used them to build more solutions. What would have happened if there was only one root? For example, what would have you done if it were lambda square minus 2 lambda plus 1 equal to 0? So the second question I'm going to write is, what can we do when there is one root? So I would like to see what you think about these two questions. Please share your thoughts on the comments. We may even have a discussion in the comment box. And see you next time. Bye-bye.